You are watching this video right now because of a cable thinner than your thumb, lying in total darkness at the bottom of the ocean, under 8,000 meters of water. You have never seen it. You will never touch it. But without it, no internet, no banking, no phone calls between continents, no stock markets, nothing. And right now, somewhere in the middle of the Pacific Ocean, a single ship moving slower than you walk is placing it there, millimeter by millimeter across 10,000 kilometers of ocean floor. It cannot see. Here's exactly how that ship does it. A cable-lay vessel is not a standard ship with cable laying equipment. Bolted on, it is purpose-built from the keel up around one function: storing, handling, and deploying submarine cable with absolute precision. A typical modern cable ship is 130 to 170 meters long, 24 meters wide, and displaces between 10,000 and 25,000 tons. The entire internal layout of the ship is designed around the cable tanks, the large circular holes that store the cable in carefully coiled loops before deployment. The ship has 3 cable tanks, large circular holes built directly into the ship's hull. Each tank is typically 15 to 20 meters in diameter and 8 to 10 meters deep. The tanks have a smooth, curved interior, no sharp corners, no protrusions, because the cable coiled inside must pay out without snagging, kinking, or suffering any mechanical damage. The center of each tank has a rotating turntable mechanism at the base that controls how the cable feeds out from the bottom of the coil. The ship is powered by a diesel-electric propulsion system, not a conventional shaft and propeller arrangement. Instead, it uses azimuth thrusters, propeller pods mounted on rotating housings beneath the hull that can point in any direction through 360 degrees. A typical cable ship has 2 main azimuth thrusters at the stern and 2 bow thrusters at the forward end. This arrangement gives the ship the ability to move in any direction, hold position in the ocean, and maintain an exact heading without anchoring. The most critical system on the ship is not the cable machinery, it is the dynamic positioning system. This is the computer-controlled system that holds the ship on its planned route automatically, without anchors, in the middle of the open ocean. The dynamic positioning system receives input from GPS receivers. The ship carries 6 independent GPS antennas for redundancy, acoustic positioning beacons on the ocean floor, wind sensors, current sensors, and motion reference units, measuring the ship's roll, pitch, and heave in real time. The dynamic positioning computer processes all sensor inputs 10 times per second and calculates the exact thrust output required from each thruster to maintain the ship's position and heading against wind, waves, and ocean current. It then sends commands to each thruster independently, adjusting pod direction and propeller speed on each unit simultaneously. The system can hold the ship within a 2-meter circle in sea states up to force 6 to 6 meter waves and 50 km/h winds. At the bow of the ship, the cable route is constantly being surveyed ahead of the ship by a forward-looking sonar system, a multi-beam echo sounder mounted on the hull that maps the ocean floor bathymetry up to 5 kilometers ahead of the ship's current position. This real-time seabed mapping feeds directly into the cable route planning system, allowing the route officer to make micro-adjustments to the planned cable path to avoid obstacles, rocky outcrops, or areas of unstable sediment detected on the sonar. The cable does not simply fall off the back of the ship into the ocean. It is controlled at every millimeter by the cable engine system, a series of powered machinery units that grip the cable and control the rate at which it pays out. The primary cable engine is a linear cable engine, a machine consisting of 2 opposing tracks lined with rubber-faced gripping pads that clamp onto the cable from both sides and drive it forward or backward at a precisely controlled speed. Ahead of the linear cable engine in the cable path, a cable tensioner unit measures the tension in the cable at all times. The tensioner consists of a load cell, a precision force measuring device, integrated into a sheave wheel that the cable runs over. The load cell measures cable tension continuously and feeds the reading to the cable engine control system. If tension drops below the minimum safe value, the cable engine automatically slows the payout rate. If tension exceeds the maximum, it speeds up, always keeping the cable in the correct tension. From the cable engine, the cable travels along a series of guiding sheave wheels, large grooved pulleys that redirect the cable's path from the cable tank, through the cable engine room, up through the deck, and out over the stern of the ship. Each sheave wheel is sized with a minimum bend radius, larger than the cable's minimum bend radius specification. Because bending a fiber optic cable too tightly permanently damages the glass fibers inside, destroying the cable's transmission capacity before it even reaches the ocean floor. The stern sheave, the final contact point between the ship and the cable before it enters the water, is a critical piece of equipment. It is a large grooved wheel, typically 3 to 4 meters in diameter, mounted on a hydraulic arm at the ship's stern that can angle up and down to control the cable departure angle into the water. The departure angle directly controls where the cable lands on the ocean floor, relative to the ship's position. Steeper angle means the cable lands closer to the ship. Shallower angle means it's further behind. Once the cable leaves the stern sheave and enters the water, it does not fall straight down to the ocean floor. It forms a long, curved catenary, an arc shape, through the water column. The exact shape of this catenary is determined by 3 factors: the ship's speed, the cable payout rate, and the water depth. In deep water, 5,000 to 8,000 meters. The cable is in the water column for several kilometers before it touches the seabed. The point where it actually lands on the ocean floor can be 3 to 5 kilometers behind the ship. The ratio between cable payout speed and ship advance speed is called the lay ratio. A lay ratio of 1.02 means for every 1 kilometer the ship advances, 1.02 kilometers of cable is paid out, leaving 2% slack in the cable on the seabed. This slack is critical. Without it, tidal currents and seabed movement would put the cable under tension, eventually breaking it. Too much slack, and the cable snakes across the seabed in loops that can tangle or be damaged. Maintaining the correct lay ratio, constantly calculated and adjusted, is one of the cable engineer's primary responsibilities throughout the entire operation. In shallow water less than 1,000 meters, approaching a coastline at either end of the cable route, the catenary shortens, and the cable's landing point moves closer to the ship. At depths below 200 meters approaching the continental shelf, the cable engine reduces payout speed, and the ship slows further. In water shallower than 100 meters, a remotely operated vehicle and ROVs is deployed from the ship to physically monitor the cable touchdown point and confirm it is landing on the planned route. The most complex phase of the entire cable lay operation is the shore end landing, connecting the deep sea cable to the land-based cable station at each end of the route. The ship cannot approach the beach directly. It draws too much water. Instead, the shore end operation begins weeks before the main cable ship arrives, using a separate shallow draft vessel and a beach team working from the shore. The beach team first installs a conduit, a high-density polyethylene pipe from the cable landing station building on shore, buried in a trench through the beach, continuing offshore under the seabed in a pre-drilled horizontal directional drill bore that exits the seabed approximately 500 meters offshore in water deep enough for the work vessel to operate. This conduit protects the cable from the mechanical damage it would suffer being dragged across the rough rocky seabed in the surf zone. The shore end cable itself is a much heavier, more armored version of the deep sea cable, because it must survive in the high-energy surf zone, resist anchor damage from fishing vessels, and withstand the mechanical stress of being pulled through the conduit. The shore end cable has multiple layers of steel wire armoring, typically 2 layers of counter, wound galvanized steel wires, and a thick polyethylene outer sheath. Its diameter is 50 to 70 millimeters compared to 21 millimeters for the deep sea section. The shore end cable is pulled from the ship through the water, through the conduit under the beach, and into the cable landing station using a pulling rope pre-ice stalled in the conduit. The operation requires precise coordination between the ship, the work vessel, and the beach team, all communicating on radio. The pull is done slowly, maximum 20 meters per minute. To prevent the cable jacket from being damaged by friction inside the conduit, the full shore pull can take 4 to 6 hours. The full cable route from continent to continent is not laid as a single continuous length from one cable tank. It is laid in sections, each section loaded into a separate cable tank on the ship. Where two sections meet, a cable joint must be made at sea connecting the fiber-optic cores of one section to the next, with zero signal loss. This joint is made in the cable jointing lab, a dedicated workshop on the ship built specifically for this operation. The cable jointing process begins with carefully removing the outer layers of both cable ends in sequence. Outer polyethylene sheath, armor wire layers, inner sheath layers. Each layer stripped back a specific length to expose the inner components. The fiber optic bundle at the core is handled only with cotton gloves. The natural oils on bare skin can contaminate the fiber surface and degrade the optical connection. The exposed fiber tubes are cleaned with isopropyl alcohol on lint-free wipes before any connection is attempted. Each individual optical fiber, thinner than a human hair at 125 microns diameter, must be fusion spliced to its corresponding fiber in the other cable end. A fusion splicer machine is used. It precisely aligns two fiber ends under a microscope camera, then fires an electric arc between them that melts and fuses the glass ends together in under 2 seconds. The splice loss. The amount of optical signal lost at the joint must be below 0.1 decibels. Each cable contains between 16 and 96 individual fibers, every one spliced individually. Once all fibers are spliced, the joint is tested end-to-end using an optical time domain reflectometer, a device that fires a laser pulse down each fiber and measures the reflection pattern to confirm every splice is within specification and no damage has occurred to any fiber along the entire length of cable already laid. A single fiber test on a 5,000-kilometer cable takes approximately 50 microseconds for the laser pulse to travel the full length and return. Any anomaly in the reflection trace identifies the exact location of a fault to within 10 meters. Fiber optic signals weaken over distance. On a transoceanic cable spanning 10,000 kilometers, the signal must be amplified at regular intervals, every 50 to 80 kilometers, to maintain transmission quality. This is done by repeaters, cylindrical devices approximately 3 meters long and 250 millimeters in diameter, permanently integrated into the cable at the factory before loading. When a repeater arrives at the cable engine during deployment, the handling procedure changes completely because the repeater is rigid and cannot bend. The repeater bypass track is a dedicated guide rail system on the cable deck that routes the repeater unit from the cable tank exit, around the cable engine, and to the stern sheave, maintaining a minimum bend radius on the cable sections, either side of the repeater throughout. As the repeater reaches the stern sheave, the ship momentarily adjusts its speed, and the cable engineer adjusts the payout rate to ensure the repeater enters the water at the correct angle. Too steep, and the cable sections, either side, are overstressed. During a cable lay operation, a fault, a break or signal degradation in the cable requires immediate response. The cable engine stops. The ship holds position. The cable already deployed must be recovered, pulled back up from the ocean floor to the fault location. This is done using the cable engine in reverse, running the cable backward through the machinery. On a deep water fault at 5,000 meters depth, recovery can take 8 to 12 hours before the damaged section reaches the surface. As the faulted section is recovered and approaches the ship, the cable is diverted from the stern sheave to a cable recovery sheave at the ship's side, allowing the cable to come aboard over the rail onto the cable deck. When the damaged section emerges from the water, the fault location identified precisely by the OTDDR to within 10 meters is cut out. A new replacement section of cable the same length is spliced in using the same fusion splicing process as the planned joints. The repair joint is tested, the cable engine resumes, and the lay operation continues. As the cable ship approaches the far end of the route, the second shore landing, the same shore end operation performed at the start, is repeated in reverse. The ship slows further. The shore end cable section, the heavy armored section loaded in the final cable tank, begins paying out. The work vessel and beach team at the second landing site take over guidance of the cable to shore, pulling the cable end through the pre-installed conduit and into the second cable landing station. once both shore ends are landed and secured inside their cable landing stations. The entire cable route undergoes final end-to-end optical testing. Engineers at both landing stations simultaneously connect their OTDR instruments and test every fiber in both directions. They verify total route loss, the accumulated signal loss across the full cable length, including every splice and repeater against the design specification. A 1,000-kilometer cable must deliver a total route loss below 2,200 decibels across all fibers to meet acceptance criteria. The cable ship's final task before leaving the area is to update the aslayed cable route, record the precise documented position of the cable on the ocean floor across its full length. Throughout the entire operation, the ship's positioning system has been recording the cable's position every 10 seconds. This data is post-processed with corrections from differential GPS to produce a final aslayed route chart accurate to within 10 meters anywhere along the cable's full length. The document that will guide any future repair ships if the cable is ever damaged. That cable, thinner than a garden hose, lying on the bottom of the ocean, under 8 kilometers of water, placed within 50 meters of its planned position across 10,000 kilometers of open ocean, will carry 200 terabits of data per second the moment it is switched on. Every email, every video call, every financial transaction between continents, all of it traveling through glass fibers thinner than a human hair, laid by a ship that moved at walking pace for 6 weeks without stopping. Now you know exactly how they do it.